So when Tycho Brahe died, remember, he went through and got all of this great data on the motion and positions of the planets. One of his assistants, Johannes Kepler, who was actually a trained mathematician, actually got all of that data on the motion and positions of the planets. From all of this data, Kepler then went through and devised 3 laws that describe planetary motion. Okay, so he actually developed mathematical formula from data to help explain how it is that the planets have to be moving around the sun. So he has 3 laws. Kepler's first law states that all planets orbit on ellipses with the sun at one focus. Now this is a break from ancient tradition. Remember, previously it was viewed that the heavens were perfect and the perfect shape is the circle, therefore planets which are in heaven must move on perfect circles. Well, to be able to explain how it is that the planets are moving as we see them here from the Earth, Kepler said, no, it is not circles, it is actually ellipses. Now, because it is an ellipse with the sun at one focus, this means that the planets actually get closer to and then farther from the sun. The point where the planet is at its closest to the sun in its orbit, this is known as perihelion, and then the point where the planet is the farthest from the sun, this is aphelion. I realize it looks like aphelion, it is not, you actually pronounce the P, it is aphelion, is the point farthest from the sun. Now, because we're dealing with ellipses, the important property of an ellipse is the eccentricity. The eccentricity describes how elongated the ellipse is. An ellipse with an eccentricity of 0 is actually a perfect circle. So what this means is that because planets orbit on ellipses, it is possible for a planet to orbit on a perfect circle. Now, it's unlikely, but it is possible because circles are a type of ellipse. As we increase the eccentricity, then it becomes more and more elongated, okay, until we have out here at a 0.99 where it's super, super elongated. Now, the eccentricity can never actually equal 1. Okay, if you get to 1, then it's a straight line and it's no longer an ellipse. Okay, so the eccentricity is from 0 up to, but not including 1. Kepler's second law states that a planet will sweep out equal area in equal time. Now, this one is getting a little bit more mathy, so let's see if we can actually break it down. So the idea is that we have the planet orbiting around the sun. If we take the planet and we draw a line from the planet to the sun, like we have here, then we allow the planet to move for a given amount of time. See how far it goes in, say, 3 days, just to throw a number out there. So in 3 days, the planet moves from A to B, and that line that we drew from the planet to the sun now sweeps out this area, making this triangle. Okay, and that is going to have some area to it. Okay, so in 3 days, it moved from A to B, and we create this triangle of some area. Now we're going to do the exact same thing again, but now at a different place in the orbit. So in this case, we're going to go from C to D. So in 3 days, the planet moves from C over to D, and we create this new triangle. What Kepler's second law states is that the first triangle from A to B and the sun is going to have the same area as the triangle C to D and the sun. Okay, these two triangles have equivalent area because they were created in the same amount of time. Now, I realize that was super mathy. So what the takeaway is that planets, when they are far from the sun, move slower than planets when they are close to the sun. Notice that the planet went from C to D, which is a much greater distance than from A to B. So planets speed up and slow down as they orbit around the sun. As they get closer to the sun, they speed up, and as they move farther from the sun, they slow down. Okay, so that's our takeaway for Kepler's second law. Now, Kepler's third law states that the square of a planet's sidereal period is equal to the cube of its semi-major axis. Yeah, you thought that the last one was getting mathy. This one is way, way worse. Okay, so What this means is we're now comparing how fast a planet is orbiting to how far it is from the Sun. The sidereal period is how long it takes to orbit around the Sun, and the semi-major axis is related to how far away the planet is from the Sun. So from this, what we're going to take away, we're not going to get into a lot of detail on this one because of how mathy it is, but the takeaway is that planets that are closer to the Sun orbit faster, complete their orbit in a shorter amount of time than planets that are far from the Sun, and it follows a very specific mathematical sequence. So planets that are close in orbit faster, planets that are farther away orbit slower. Now, I realize that this sounds a little bit like our takeaway from Kepler's second law. However, make sure you get this difference. Kepler's second law is looking at a single planet and how that one planet is orbiting around the Sun. When it gets close, it goes fast. When that planet goes far away from the Sun, it goes slow. Kepler's third law deals with two different planets, comparing them. And it states that a planet that is closer to the Sun is orbiting faster than a planet that is farther away from the Sun. So make sure you get the distinction between those two. Now, using Kepler's laws, this actually helps us understand more than just the motion of planets. Using Kepler's laws, we can now predict the planetary motion. We can predict exactly when and where a planet is going to begin and end its retrograde motion. In other words, this is a huge leap forward. However, as we've studied more about the universe around us, we actually see that these laws that we have from Kepler actually apply to more than just planets orbiting the Sun. It also applies to planets orbiting around other stars than our Sun, what we refer to as extrasolar planets. This also applies to moons orbiting around planets, and stars orbiting around each other, and to some extent, although it's not perfect, and we'll get into it more later on when we talk galaxies, even some stars in galaxies tend to follow this motion. Alright, here is our fourth lecture quiz question. Which planet moves the fastest in its orbit? A. Jupiter, B. Uranus, C. Pluto, or D. Earth? Go ahead and think about it, and we'll discuss in just a bit. Alright, so which one moves the fastest? The one that goes the fastest is going to be whichever one is the closest to the Sun. And among this group, the answer is D, the Earth. Earth is the planet that is closest to the Sun from this selection, and therefore it's going to orbit the fastest according to Kepler's third law.